This presentation will discuss how fog computing can be used to assist in smart traffic management. We will first begin with a basic background of the necessary information and then move on and state the issue that we wish to solve. We will then provide information about the various articles that we have researched and move on further to provide our solution and our plans for implementing the solution that we are suggesting. Before getting into the specifics of the issue that we wish to deal with, we first have to explain what we mean by smart traffic management. A term that is constantly thrown around these days is a smart city. Now, a smart city is essentially just a way of saying that we use technology within this city to improve upon the daily lives of the city's inhabitants. The ancient Romans applied the concept when they were using things like aqueducts and roads to help their citizens have easier lives. Now, obviously, in today's modern times, we use far more sophisticated technologies in order for our cities to be considered smart cities. Essentially, what we use to make our city from a regular city to a smart city is data. By collecting data from around the city, we can pick up patterns and a feeling for what our citizens need in the city. The first city that really officially did this was Amsterdam back in 1994. By using small electronic sensors around the city, data is able to be collected around the city to give us a better feeling about what the city needs. With the development of fog and cloud computing, cities have changed their methods of how to collect and store data about their cities. Cities can now use cloud and fog computing technology to record and track data about environmental activity and also other information about their infrastructures and their residents. Furthermore, the creation of fog and cloud computing technologies has also changed how devices are built. In addition to the actual functionalities of various devices, internet connectivity is also now being taken into account to allow these devices to connect to the internet. More and more devices are connecting to the internet, and by the year 2020, it was estimated that around 31 billion devices were connected, and it's expected that we will surpass the 100 billion mark by the year 2030. Now, more and more devices are being connected to the internet, which means that the recording of data is coming from more and more sources. And while on the one hand it may seem like that this is a very positive and good thing, there are potential drawbacks to this situation. Before we discuss in detail what these drawbacks are and how they can be fixed with fog computing, we'll first discuss and explain just a basic background of what cloud computing is. The term cloud computing simply refers to the idea of sharing resources and information over a network. Data is stored and maintained on a server by a service provider. And this data can be accessed via an internet connection to a personal computer. This personal computer is known as the user. This three-step process, being the user, the internet connection, and the data in the server, is all known collectively as the cloud. Although cloud computing has certainly been very useful, and there's many pros, many benefits that come with cloud computing, there are certain drawbacks that come with cloud computing that might not make it the best choice. Now, although there are a few issues with cloud computing, the issue that we're going to hone in on for the purposes of our presentation is latency. Cloud computing tends to have high latency issues. And there are several factors that can assist and be the reason for this problem. First and foremost, the reason why cloud computing can have high latency is because since all the data is going to one central server, all on one channel, all in one network, one one highway. So the length of the trips and the number of trips that the data packet may need to take can cause high latency. Furthermore, due to the virtualization of data centers, packet delays may be experienced even before the data can leave the server. And also, due to the increased use of distributed computing, so if one of the servers on the network experiences high latency, this can also have an effect on the other servers as well, which would result in a slower performance. Now, fog computing runs differently than cloud computing, and we'll get into the differences between fog computing and cloud computing more extensively later on. But for now, just to point out how, in a very basic way, how fog computing can help pick up the slack where cloud computing fails. A very basic overall difference between fog computing and cloud computing is that fog computing uses a decentralized system as opposed to cloud computing, which uses a centralized system. To be clear, fog computing isn't a replacement for cloud computing. Fog computing is added on to the cloud computing structure. It is put in place in between the user and the servers that make up the cloud. And this decentralized approach that fog computing uses gives fog computing several advantages over cloud computing. First and foremost, fog computing has higher security because all the data that a user may be receiving and sending is going along a much more complicated and complex path to the ultimate server. And this makes it much more difficult for other people to hack the data or to steal the data, as opposed to cloud computing, where everything is essentially just going on one highway to the server. Additionally, fog computing makes it virtually impossible for a user to lose connection with the server, because due to the fact that there are multiple nodes in this decentralized system with fog computing, so even if a user were to move out of one area, they will automatically be within the area of another node, as opposed to cloud computing, which can have some rough patches and weak spots in the network. And this leads right into the next point of how fog computing leads to also lower latency, because since there's less time, there's less space, less distance for the information to travel to the nodes. So this makes things work much more quickly. And this obviously results in higher user satisfaction, as opposed to cloud computing, where the data can oftentimes have long distances to travel. With all these benefits of
As we already discussed in the introduction section, how we use traffic management systems to solve traffic problems in large cities, we're going to dive into how traffic management systems refer to broad range of related interconnected systems. Traffic management system usually falls under two categories, which are infrastructure free and infrastructure based. The infrastructure free can include cooperative congestion detection, congestion avoidance, and accident detection and warning. The infrastructure-based traffic management system include traffic light management, route suggestion, congestion detection, and rerouting speed adjustment. Traffic management system consists of a network of endpoint devices, typically vehicles, roadside units, and at base stations. The vehicle nodes and roadside units take in data and communicate to each other using a variety of routing protocols, topology, and novel algorithms to increase the efficiency of traffic flow. The data collected is then sent to the base station. From here, the base station may forward the data to a centralized site, that is the cloud data centers, where it can be processed and stored. Communication can also happen in an ad hoc fashion between the end node of vehicles, which is the V2V. This is commonly referred to as vehicle ad hoc networks. The fast-paced, dynamic nature of traffic, along with government regulation, require that any management system may be reliable, accurate, secure, and low latency. So now we're going to dive into traditional cloud architecture versus fog computing. So cloud computing began to develop to what we know today. Back in the 1990s, a professor in Emory University defined cloud computing as computing paradigm, where boundaries of computing will be determined by economic rationale rather than limits alone. This will prove prophetic when Amazon launched its first Amazon Web Services in 2006, which became the gold standard for cloud architecture. What followed was a revolution in computing wherein a person or a business no longer needed to pay for and maintain their own premise service. Elastic service platforms or service that can scale processing capabilities based on demand could be deployed in seconds across a wide geographic area. This led to the software as the service model in business. This has led to the software as a service, which is known as SaaS model in business. Today, there are countless applications that permeate all areas of society that use the cloud in some form. Companies like Netflix, Gmail or Google, Salesforce, Slack, Zoom, all use cloud-based architecture to satisfy their data processing and storage needs. Even Microsoft Office, a staple of traditional packaged software, now offers SaaS, which is the software as a service model based of their tools online. It is apparent that the advent of the cloud has created the paradigm shift that the professor in Emory University stated it would. When it comes to fog computing, fog computing is a generic term for a form of distributed infrastructure that allows smart devices at the network's edge to handle certain application processes. Fog computing is an abstract form of fog computing is different as it only stores data that is frequently accessed by users, while it takes the rest of the data from the cloud. Fog is efficient in data processing as it acts as a middle layer between the hardware and the cloud. Therefore, fog computing acts as a firewall by adding a layer of security to the cloud. Fog computing faces security challenges such as authentication, malicious attacks, end-user privacy, and secure communication. Meanwhile, traditional IT infrastructure consists of hardware such as desktop computers, which are linked via remote server to form a network. Typically, For systems that leverage for computing, the most sensitive data will be processed near the edge. Data that is the middle of importance can wait seconds to minutes, can be passed to a middle node for aggregation, pre-processing, and analysis. Finally, data that is the least time sensitive can be sent to the cloud for big data analytics and historical storage. The system just described improves upon traditional cloud architecture in several key ways. The first is the aforementioned reduction in latency. Another benefit in the reduction in bandwidth usage. As larger portion of the data are handled near the edge, the amount of data that needs to be transmitted is reduced. This allows for the added benefit of lowering maintenance costs. Now we're going to look at the difference between fog computing and cloud architecture. When it comes to fog computing, latency for computing is low, while cloud computing has high latency. Fog computing provides a high level of security, whilst it is possible to integrate multiple data sources and devices into fog computing. While it is possible to combine just multiple data sources when it comes to cloud architecture. The amount of data sent to cloud computing is reduced with fog computing. While sending or converting data, cloud computing does not provide any data reduction. A large number of server nodes are used in fog computing, whilst there are a limited number of server nodes in cloud computing. The system has high response time when it comes to fog computing, whilst the system has low response time when it comes to cloud architecture. In fog computing, mobility is supported, while mobility is limited for cloud computing.
So far, we've already defined what cloud and fog computing is, the advantages and drawbacks, and how they're used. So now we'll look at some research articles that discuss this topic in depth and how these authors support fog computing, especially when it comes to our topic of vehicles and traffic management within smart cities. Traditional IT infrastructure requires consistent upkeep and work by IT professionals at physical data centers, which is considered expensive and it's a waste of time as opposed to cloud and fog computing. And I just wanted to share this little table that lists some of the current smart cities and the infrastructure they have, as well as what Amazon service provides and what two researchers, Gonchev and G, suggest. Now, in this article, it's mentioned that Padova uses a central server that collects data, and it also does the processing and allows for user access. And Trento should be the same as well. Wuxi is centralized by provided services using several applications, and Seoul is similar in that it uses a group of servers for organizing and processing data. And Melbourne, Amazon, and Ganchi and G rely on structures based on a central server in the cloud. So those are just a few examples of what some smart cities are doing. So Baldessari found prior research that addresses the constantly growing population and the huge problems seen with travel and transportation as a result. One of the main goals of smart cities is to mitigate heavy traffic by informing drivers on how to avoid heavy traffic areas and what routes are better. To meet this goal, Baldessari created a prototype that would use a cloud paradigm that takes information from live camera feeds, historical data about the city traffic, and data from sensors. However, he didn't actually run an experiment on this. He just wanted to point out that cloud, due to its scalable storage, could be a good option. However, what he failed to discuss are the limitations seen with cloud, for example, big data and speed. The general consensus of the other articles we found was that the implementation of fog would be better than just having cloud. The reason being that, as it's mentioned in another article here, fog-based smart cities would bring about location awareness, low latency, cost reduction, and heterogeneity, which Baldessari didn't really explore in depth. Therefore, a number of researchers found that fog could fix the limitations that cloud-based cities faced. Kunal and his team, for example, focused on fog and real-time analytics. Real-time analysis is important, especially when decisions have to be made right at that moment, for example with traffic lights, which we'll talk about later. Also, fog has its own share of problems, like with privacy concerns and data security issues such as authentication, malicious attacks, and user privacy and secure communication. But still, the pros outweigh the cons in this context, which are seen in the 3 fog-based examples Kunal pointed out to prove its efficacy. So we see here data from manufacturing IT systems to financial institutions, another one being modern electric grid systems, in which data about electric consumption from a remote location could be sent immediately to an electrical production data center. And connected cars is in reference to self-driving cars. The kind of data that is generated and processed are based on a multitude of things like weather conditions and traffic, just to name a few. And specific information about the cars can be sent to the manufacturer. So this goes to show that real-time processing can be achieved with fog. And so this further brings us to the discussion of cars. In the article with Visa, his team mentions that cars nowadays receive updates from their manufacturers, but there is the problem of updates being delivered too slowly. Therefore, they suggest having fog nodes distributed all over the city, and that would allow the cars to quickly receive these updates. And the authors here formulated an algorithm for accomplishing this, and in this algorithm, a car will reconnect with a new node as it leaves the vicinity of an old node, which is done by having the car monitoring the connectivity strength with the old node. And if the strength has dropped below a certain level, then the car will connect to a new node. The idea of widely distributed fog nodes is something agreed upon by some other articles we've come across, like for example Kasim's article. With regards to this topic, he says his fog-based prototype design would focus on real-time processing, scaling, access, cost reduction, and heterogeneity, as we've mentioned earlier. In his attempt to show this, he ran an experiment that involves the simulation of a parking and monitoring system with the help of iFogSim, which is a simulation tool. The goal here is to show that fog can update drivers real time about what areas are crowded, what path to take, what parking spaces are currently available, while also helping with traffic monitoring. This would prevent cars from crowding an already crowded area, helping them to save time rather than going in circles to find parking. And users use a mobile app that connects them to this information. So here are the results from this experiment in comparison to just using cloud. As predicted, with fog there are less delays and fast responses when using real-time applications. If additional devices are constantly added, it shouldn't be an issue since it doesn't increase the delay. In fact, it just adds to the reliability, interestingly enough, and it even allows for smooth data transfers. However, cloud has less delays than fog when looking at user interface delay, but it's really not a big deal at all since this kind of delay is not considered useful or important at all, so we can just ignore it. We can also see that with the fog-based architecture in this experiment, the network usage and costs are much less than cloud. One slight issue with fog is that as more devices are added on, there will be more energy used. This next article looks more in depth about traffic delays and how to prevent them. The authors in this article experiment with traffic simulation, also using iFox Sim, in trying to prevent traffic jams. And so they presented something called FogFly, which is a fog-based method in which there would be fog nodes placed at various areas of the city and also at traffic light control units in order to control the traffic light signal timing. They also created computational models that would figure out at each intersection where a car comes from, like from which lane, also did it turn from the left or right. It would also calculate how many cars are on a lane at a given time, how long does it take for the light to turn from green to red, as well as traffic volume and flow. So here we compare FogFly with a cloud approach, and we can see that there is much lower latency with FogFly than with cloud. With energy consumption, this method shows that centralized data processing with cloud consumes more energy than having a few nodes in FogFly. And then we also see here that the more fog nodes there are, the more energy consuming it is. And we can see that using FogFly is more cost effective as well.
So looking into some of the current research into transport management system applications that utilize fog, Bardwaj and Gundar proposed a fog-based traffic management system that used a hierarchical distribution of fog nodes. Their research found that end-to-end processing was reduced by 77%. It also reduced the average number of hops by 52% and reduced the bandwidth consumption by an average of 96.7%. Flaviana Pisani et al. They also analyzed a different system where the fog nodes would filter data at the edge before sending it up to the cloud. They used a mathematical model to determine if data was necessary to be sent upstream, and their research found that it generally reduced the cost, except for in certain outliers. They also found, though, conversely, that it did increase energy consumption. Jyoti Grover et al. They assessed the need for real-time computations in relation to transportation management systems. So the system they proposed used what they called foglet servers, which were they were small cloud-based servers localized within cities. They would use roadside units to connect vehicles to the larger network. Arnav Thakur et al. argue against a large round-trip time and centralized approach, i.e. a traditional cloud-based architecture. The system they described was a vehicle-to-vehicle and a vehicle-to-infrastructure types of network, and they provide a statistical model for making traffic routing decisions. So our proposal is to create a multi-tiered fog-based traffic management system. The system would use a hierarchy to disseminate information. It would achieve this by utilizing 3 unique components. The first described as roadside unit clusters, or FRSUs. The second being localized vehicle level preprocessing, and the third priority packets. So this is an overview of the architecture. At the highest level, you can see we have our traditional cloud data processing centers. They would be connected to a cellular base station that would utilize a MIMO, or a massive multiple input, multiple output antenna. They would connect to the cloud data center via 5G wireless, ultra reliable, low latency communications. They would also use the 5G to connect to the fog roadside unit clusters, or FRSUs, which could then connect to the vehicular networks, which would likely be in an ad hoc style. They would use an IEEE 802.11p or Wave Wi-Fi to connect to the vehicle networks.